And so let me kind of give you the agenda for today. So today is going to be, the task of today is to talk about tasks. And I'm going to start off by kind of introducing a kind of motivating argument for using tasks. And I'm going to, this is maybe a little bit historical in that I'm going to talk about some earlier work. Then I'm going to talk about the conceptual issues that come up when you want to think about tasks instead of skills and how they might be related. And then I'm going to go from there and give you some examples of some very recent work by myself, but primarily by others, using a task model to understand changes in occupational wages, changes in employment across countries, and also changes in well, actually, those would be the two motivating examples for this part. Then I'm going to finish up the sort of initial use of tasks for describing wage structure changes, and then I'm going to go talk about trade, and I'm going to come back to the issue we talked about yesterday with the Che and Wu paper about how what happens in the data makes sense, but what the model says doesn't really fit. And I'm going to introduce an alternative model, or a really complementary model, which is the Grossman-Rossi-Hansberg model of trade and tasks, and show you how you can use that model to interpret what's happening in the Che and Wu paper. I'm also going to show you that model, in fact, is isomorphic to the one that we did yesterday, and I can show you exactly how you can map their results back into the standard learner diagram that we drew on the slides. But this may still be a very useful way to think about it. Then I'll actually present you some evidence on trade using a task view to understand foreign direct investment versus exports of goods. This is from another recent working paper by a UC San Diego student. And then from there, I'm going to talk further about task and the division of labor within organizations, and how firms might decide how to allocate, or how to create jobs, or not create jobs, but how to allocate tasks across jobs within a firm. In other words, whether they should make jobs be narrow, consisting of just one task, for example, or broad, consisting of multiple tasks, and what are the actual trade-offs there. And there I'll be talking about a paper by Desan and Santos in the JPE a couple years ago called Adaptive Organizations. Then finally, at the end of the day, in the third lecture, depending on how far we get, I'll give some other recent examples. One, I'll talk about a recent work by myself and David Dorn about looking at task change and changes in employment by age, as a way of kind of measuring changes in job composition and how they affect people at different points of their career. And then I may or may not get to work on immigration and skill mix and technology, which builds on papers by Patricia Cortez, who is a student of mine, has a paper in the Journal of Political Economy in 2008 on immigration and prices in local labor markets, or in local markets, and also work by Ethan Lewis of Dartmouth that looks at immigration and demand for high technology manufacturing processes in manufacturing industries, in cities, in manufacturing industries in cities. Okay, so that's the kind of agenda. Yes?
Is there a list of all the articles you're presenting?
I think so. What I can do, so everything that I present is listed, so I cite them in the slides, and I can send the slides to you, and then we can put them up, right? And then if you look further on my webpage, my MIT webpage, you'll find my graduate lecture notes and syllabi, and those also detail these things. Most of these things I work through the models more completely, and I list the papers. But actually, some of the stuff I'll talk about today is new enough that it hasn't hit my graduate lecture notes yet. In fact, it just got organized this morning, so and read on the plane here. But so that I will refer you to the slides. But yes, thanks. It's a good question. Yeah, and I do cite them in the slides. Okay. Other questions? Okay. So as always, I encourage you to jump in with questions, and that's helpful to me. Okay, so let me start off with a figure that I ended with in the end of the first lecture, yesterday, which was looking at these changes in wage percentiles, and this is from US data, and this just contrasts the period of the 1980s where wage inequality growth was monotone in skill, and the period of the 1990s where it's sort of U-shaped, or some would say polarized. And this is kind of a startling development, and I think a lot of the literature that was sort of trying to understand wage inequality, up through the late 90s and early 2000s was really focused on these facts and was unaware of how the facts the facts had changed, or at least not what had happened in that period, but how the trends that people would have projected looking at the data at that point were not going to continue. Here's an even more dramatic example of that. This shows you, this is from a recent paper by Faripeau, Fortin, and Lemieux. This is one of the brand new ones. And in fact, I think this paper was just presented last week for the first time at LSE, and I only learned about it because one of my co-authors was Googling and found it. And then I wrote to the authors and said, could you send me this paper? And so that's why I have it. So anyway, this is this looks at changes in wages by occupation in the US data from basically the mid-1980s to the early 2000s. And here on the x-axis is the base period wage of each occupation, and on the y-axis is the change in wage within that occupation, right? And occupations, right, just to be clear, occupations are just, might be a clerical worker, manufacturing worker, air traffic controller, plumber, etc. And what you can see, and this is a scatter plot where the circles correspond to the size of the occupation in terms of employment. This is a quadratic fit of that relationship. And what you can see, quite remarkably, I think, is this kind of U-shape where high wage occupations, in other words, occupations that were paying high wages in the mid-1980s, show substantial wage growth, as do low wage occupations. But in the middle, you see these declines, right? And these are, I'm pretty sure these are real wage declines. These are not just relative, right? So in other words, you do see declining wages in the middle. Another closely related to that is, or another way of looking at the same thing, is to look at changes in employment shares. So the previous one was wages. This one's employment shares. And this is changes in employment shares by skill percentile, and these are again ranked by occupational wage. So here, now going back to my own data, this is using data from the 1980 and 1990 census and the 2005 American Community Survey, which is basically a survey that's related to the U.S. Census but occurs more regularly with smaller samples. And so what's done here, and this is in work with David Dorn, we rank occupations by their mean wage in 1980, and then we look at the changes in employment share over the next time interval. And what you can see is in the 1980s that employment growth is strongly monotone in wage percentile. So high wage occupations are growing as a share of employment, low wage occupations are contracting. These have to integrate to zero, right? These changes in shares have to integrate to zero. And then this shows you the more recent 15 years. And here you see that basically occupations below the 25th percentile in terms of wages, which we sometimes call skills, are growing. And occupations above the 60th percentile are also growing. And then these occupations from essentially the 60th down to the 20th percentile or so are contracting as a share of employment. Okay, so putting these things together, it's pretty striking actually that in the period in which wages are growing monotonically in percentiles, employment is growing monotonically in wage percentiles, i.e. in the period when low wages are falling, low skill occupations are declining in employment, and in the period in which wages are rising, high skill wages are rising in employment, as are wages in those occupations. And then in the more recent period, the last 15 years, right, you have growth in wages at the bottom, growth in wages at the top, and growth in employment in low wage occupations, growth in employment in high wage occupations, declines in employment in middle wage occupations, right? So looking at those two things, it's hard not to think that they're related to one another, right? That in some sense there must be some net demand forces that are basically changing quantities and prices in the same direction in both periods. Now that's a very, very loose statement. I just want to be clear because we don't think that each skill percentile or each occupation is an independent labor market, right? We don't know how substitutable or complementary they are, right? So it's not, you wouldn't want to regress change in wage percentile and change in occupation percentile, skill percentile or employment share and call that any type of structural relationship. It's merely a suggestive trend, okay? I just want to be clear about that. But nevertheless, it's very striking. And so people have referred to this sort of relationship as polarization. I think Goose and Manning are the first authors to actually use that term. And so what I want to talk about now is, first of all, sort of evidence, just descriptive evidence on how common this is across countries, and then I want to talk about explanations for it. Okay, but the reason I put this up at the end of the first lecture yesterday was that I don't think that you can understand this non-monotone growth of wages and employment by skill in the simple two-factor model that I was using at the end of the last lecture, right? That essentially that model really, if high-skill jobs are at the top and low-skill jobs are at the bottom, you would not get this kind of U-shape, right? It has to either be things are either pulling together or pulling apart, but there's no middle skill, and so you need a richer model. It doesn't have to necessarily be a richer model of skills, but it needs to have some other intermediate layer to interpret this, and so that's where I want to go. But before I do, let me just give you a few other pieces of evidence on this. So this is from the paper by Goose and Manning in 2007 called Lousy and Lovely Jobs, the Rising Polarization of Work in Britain. And what they do is, in this picture, they just rank jobs in 1979 according to their job quality, which really I think is pretty much wages. And then they look at the changes in employment shares over the next 2 decades using the LFS, Labor Force Survey. And what they find, consistent with the US data, is growth in high-quality jobs, high-wage jobs, growth in low-wage jobs, and then relative declines in middle-wage jobs. And here's a kind of a less clunky version of the same, but it really is the same thing, so let me skip it. Here is from a more recent paper by Goose and Manning and Anna Solomons, and this is a working paper, and they use harmonized European labor force survey data from 1993 to 2006 to try to look at the prevalence of and determinants of employment polarization across 16 EU member countries. And let me, so one thing about their data, so some strengths and limitations. The strength is that they have harmonized employment data. The limitations is they don't have harmonized wage data. And this is often, right, as many of you know, work in this area, it's much easier to get consistent employment than wage data, although when we say easy, it's not cheap, because there seems to be a view that you should charge for data by average cost rather than marginal cost in Europe. And so I know they paid a fortune for these data. If it were, I would say the US has many dysfunctional elements, but the government does give data away, which we think is a good thing. Anyway, so they break, using this group of, I guess it's 21 occupations, they break them into the 4 lowest paying, the 9 middling, and the 8 highest paying. Now, why do they do this in terms of, why do they break them so unevenly? Well, basically they have in mind the bottom quarter, top quarter, and the middle 50 percentiles, right? And then they ask, looking across countries, where do you see growth in employment within these distributions? And basically, on average, you see that the lowest quartile is adding about 1.58 percentage points in employment share over this period. The top quartile is adding about 6 percentage points, and the middle is declining by about 8 percentage points. And if you look across countries, you'll see that in almost all countries, I think in 14 of 16, the middle is declining relative to the other two. So its decline is, or let me say, the growth at the tails is more positive or less negative than the change in the middle, right? So that you have this kind of pervasive pattern of rising employment in low-skilled and high-skilled jobs simultaneously. And here's a kind of a plot of that from their paper. And I want to say, so the fact that you see this consistency across countries, I think, is a really useful and important starting point. Because if you think, going back in time 10 years to the sort of the initial literature on inequality and skill bias technical change, right? It was very, very focused on U.S. data. And it fit the U.S. data very, very well, not surprisingly. And I showed you in the Cardin Lemieux paper yesterday, right? It fit Anglo data quite well as well, right? So if you look at Canada, the UK, and the US, and it's easy to explain them with sort of a common set of models. But as people looked across other countries, they concluded that the patterns were much, much less consistent. So the most consistent thing you could say is that educational premiums stopped falling and either plateaued or rose across the OECD in the 1980s. But if you want to look for evidence of kind of monotonic rises in wage inequality, they weren't so pervasive across countries. And for a long time, kind of the two countries that were given as counterexamples to this phenomenon of biased wage and employment growth were France and Germany. Which were, obviously two largest economies in Europe, neither of which seemed to have, rising wage inequality. Now, it turns out actually that Bernd Fritzenberger had discovered in his thesis a long time ago that in fact there was rising wage inequality in Germany, but he hadn't notified, the Wall Street Journal, so it hadn't gotten out. Recently, a paper by Dushman, Lüjdek, and Schoenberg actually finds something very, very closely related, using more up-to-date data, that there was in fact growing inequality in Germany. But nevertheless, I think that literature kind of lost a lot of force because I think the view was if it's a technological phenomenon, right, then it should be shared across developed economies. And so we should be looking for similar patterns, or at least an explanation that could simultaneously accommodate the different experiences of different countries. And so I think, so it's very nice as a starting point. Yes, Alexandra?
I don't know, maybe has anybody ever looked at whether it is the same occupations that are in the low part of the wage distribution in the US and Germany, for example?
Yes, I think the rank, and this comes out in the Goosen, Manning, and Solomon's paper, that the ranking of occupations across countries is very, very similar. So the wage differences among them are not necessarily, right? I mean, wages are much more compressed in some countries than others. But in terms of just sort of the ranking, so if you just do the rank order correlation of wages, so rank occupations from top to bottom in each country, those are extremely highly correlated. Right, so it's the case that waitering and waitressing jobs pay very low, engineering jobs pay very high, and that's true across all countries, or relatively true across all countries, right?
And how big are things over time? So the lowest paid occupations in '96, are they the same as in 2002? Or
pretty much, yeah. Pretty much. I mean, basically, and you'll see this, the lowest paid occupations in almost all countries are jobs that are basically in-person service occupations that don't require extensive formal education, right? So there are things like cleaning, table waiting, security guards, low-skilled kind of medical aides, like people who come to your house and help you take your medication or something like that, right? So those are kind of lowest paid occupations across almost all countries, and there's and probably a reason for that is the supply of skills to those activities is extremely elastic, right? In the sense that they don't require, they just require basically, eye-hand coordination, spoken language, and the ability to, show up in a place on time. But they don't require any other, formal training. Middle skill occupations tend to be things that are either production positions or kind of office clerical positions, right? So things like secretarial work, accounting, filing, and things that are, and also some degree of sales work. And then moving up from there, higher wage occupations tend to be things that are either professional specialties like medicine or nursing or computer programming. And then moving up from there, you have things that are professions, so like law, doctors, academics, judges, and those are, or scientists and engineers, and those would be the highest paid occupations. And that sort of categorization is very comparable across countries, right? And they're highly correlated with educational requirements of occupations. But as you'll see, the relationships with education become non-monotone later on. Yes, Michael?
Is there a feeling, I mean, we have this view that institutions matter. So if you have
Yeah.
kind of
Yeah. Right.
institutions or regulations, regulations, wouldn't they kind of screw up this because you'd expect?
Sure. So I mean, So yes, absolutely. So I think that a problem in this literature, right, is, I said, well, one reason to start with supply and demand is it explains a lot of the data. Another reason is because we don't know how to measure institutions, nor do we know how they're supposed to do, what they're supposed to do in the labor market. So it's much harder for people to simultaneously evaluate the role of market forces and institutions, right, and their interactions. In the papers, actually, in both the Goose, Manning, and Solomon's paper that I'll talk about, and the Lemieux, the Ferpo, Fortin, and Lemieux paper, they both make different efforts to explore the role of institutions. So the Ferpo, Fortin, and Lemieux is just US data. They talk about the role of unionization or deunionization. Goose, Manning, and Solomon's is EU data, and they're going to measure institutions as a function of essentially wage compression. So they're going to say countries that have more compressed wage structures have more institutional forces acting on them. Whether that's true or not, I'm not sure. And so both of them will make some effort to evaluate that. But actually, it's a very good point. So the point I want to make about this commonality of trends is it provides a good starting point for analysis, right? Because if we see something similar happening across a lot of industrial economies simultaneously, we can hope to develop a set of explanations that are not simply country specific, that don't just fit one country, and may have the hope of explaining more facts. Now, I said these facts are about employment changes. They're not about wage changes. So the wage changes we have much, much less information on, and I wouldn't be at all surprised if they're less consistent than the employment changes, right? And so, and I think that will be something that's open to interpretation in this literature, right? So this comes back to a couple points. So one is, I think it's come back to what Michael was saying a moment ago, if the wage changes aren't similar across countries, why would the occupational changes be similar, right? Obviously, these things are not determined independently, right? Obviously, you would expect that if output of an occupation becomes cheaper, you'd expect to see more of it. If it doesn't, you'd expect to see less of it, and so on. So it's actually, if we find that there's commonality of occupation changes but not commonality of wage changes, we have to ask why, right? And I think the answer is that we don't know, and the literature hasn't really gotten there yet, right? So basically, all we know, or all I'll be able to say today with some confidence, is that there's commonality of occupational changes, and the wage side of that still is to be explored, right? But my prior is that the wage side will be much, much less consistent. But I still think actually this is still hopeful, right? Because you might think, well, even holding wages constant, employers are going to adjust the mix of things they do as suitable for their customers, for their products, for their technologies, and so you would still expect to see some of that. Yes.
But I think that the employment numbers are consistent with the view that there's a minimum wage binding in a lot of continental European countries because they've got the largest growth of employment share. Like France, Germany, Portugal.
Yeah.
These are Spain. These are typical countries where you think there's a kind of a binding minimum wage,
right?
Social minimum. In the UK, much less. So the wage is taking up some of that slack. If you think of things coming from demand, it's consistent with your.
But I guess you might have expected, right? If wages are very high in those occupations,
They're rigid. So
right? But if they're rigid,
then you can get more employment. So it kind of supports the story.
I see.
Maybe it doesn't work for France, but it works for Germany. Germany and.
Okay, for Germany. Okay, all right. So this. Oh, I see. I see.
I'm looking at the share.
Okay.
It's kind of a.
Okay. All right. So we'll get there. Okay. But I think it's. So all I want to say for now is the commonality of trends across countries, gives us a starting point to work with. And the wage side is something that needs to be understood, and I think a lot of it awaits better data. Okay, so now I want to motivate a way of conceptualizing this problem, and I'm going to sort of talk about some of my own work here, and I'm going to give you some very rich examples that I hope will be useful. This is really a kind of review of my work with Levy and Murnane. And we were trying to understand technology and skill demands, and we were very unsatisfied with this notion of technological change is skill biased because it is. We felt that it was sort of a content-free hypothesis, and basically was really a data-driven hypothesis. That basically, in the period in which you saw a lot of computerization, you saw a lot of growth of wage inequality. So it must be that computers are, demanding of skills. And we felt that that was really not a very satisfying hypothesis, and didn't really have a lot of content. And if you asked, if you tried to explain, well, what was it about computers per se that raised demand for high-skilled workers and lower demand for low-skilled workers, it's really kind of hard to say. You give the example of word processing, and people are like, well, that doesn't seem very, doesn't seem like to have a lot of broad applicability. What's going on? And so we felt that we should try to put a little more structure on this problem. So we said, well, let's, instead of thinking about skills, let's think about tasks. Now let me make a distinction here that I think is important. So a skill is a stock of human capital that you either you are born with or that you acquire, right? And it's an investment good in the sense that you can acquire more human capital. And so it's governed by, as an investment good, it's governed by a set of economic relationships that are, best described by perhaps like the Mincer-Ernst equation, right? Which is that says in equilibrium, the return to a year of education needs to be roughly equal to the interest rate. Right? And the reason that's true is you need to be compensated for the opportunity cost of having spent an additional year in school. The foregone earnings, essentially a year of earnings discounted forward. And so to make you indifferent between different levels of education, we essentially, in equilibrium, the market needs to compensate you at about the rate of interest for your foregone earnings. Right? And that's an empirical regularity. It's incredibly well documented. It's been one of the great empirical successes of economics, I think it describes well the relationship between schooling and earnings. However, you might what we wanted to motivate the idea is that a skill is not the same as a productive activity, right? So a skill is something that enables you to be productive, but a skill is not what you actually do at your job, right? You don't do college education at your job. You do a specific set of tasks that taken together produce output. And a task is very different from a skill in that a task is a choice variable at any point in time. What task do you do at a point in time? And it's not a stock, right? It's kind of a flow of work activities. And you may have capabilities at many, many tasks, right? And the ones that you choose to do, right, are a function presumably of what your capacities are at those tasks and what is the market return to those tasks, and you'll allocate effort across tasks according to utility maximization or wage maximization, and depending on the the way tasks are combined for work, you may or may not use all of your, quote, skills at a point in time, right? You may not, all the things that you could potentially do, you may not be doing at any given moment, right? So you may have skills as an economist, skills as a gardener, skills as a motorcycle mechanic, and skills as a performance sailing racer, right? But at a point in time, in the skills model, in the canonical skills model, all those things would need to be compensated in the labor market. You'd have to be paid for the opportunity cost of those skills, even if you weren't using them. But that may not be the right model. It may be that you're only going to be paid for the things you're actually doing, and in which case wage setting would look very different. But I'm getting ahead of myself, so let me step back. I just want to make the distinction I want to make between tasks and skills is simply that a task is an application of skill to a specific activity. Okay? So we want to say, well, how does computerization or other forms of technological change, how do they affect job tasks? And then so we're going to start with task demands, and then we're going to try to map them into skill demands, and then talk about what that might mean for labor demand. Okay, so before we go there, I just want to kind of talk about automation or technological change in kind of a larger perspective. So I said yesterday, I talked about Tinbergen in his idea of the education race, that basically technology is always and everywhere skill biased, and so as technology advances, demand for skill rises, and then if supply of skill keeps up with it, wage inequality stays constant. If it doesn't, it rises. If it gets ahead of it, it falls. Well, I don't think that view is adequate to understand the sort of broad sweep of technological change. So if you sort of think about the different eras, so the first kind of major era of recent automation going back a few hundred years is the substitution of basically either animal power or machinery for human musculature, right? So basically, the horse-drawn plow, steam and water power, electricity and fossil fuels, and these were initially, what they were used for was to basically take raw human labor and substitute it with other forms of energy, right? Other forms of physical input. And that would have been a skill-biased technical change in some broad sense, in the sense that it would have reduced the value of brawn, of musculature relative to cognitive ability, in the sense that all of a sudden the supply of brawn from alternative sources becomes much, much cheaper. And so that, as a source of comparative advantage in the labor market, that would be less significant. It would be put a greater weight on other skills that you might need. The second recent stage of automation begins with the kind of what people would call the era of mass production. And mass production was the problem of trying to take artisanal tasks, i.e. tasks that took a lot of handiwork, so making of fabrics, making of guns, making of bicycles and sewing machines, and turning those from a kind of an individual handicraft into a machine automated production process. And that was an extremely difficult problem, right? The idea, so the kind of the goal of mass production was really often thought about in terms of the goal of creating so-called interchangeable parts, right? Parts that were so precisely machined that you could take a part off of one object and a part off another object and swap them and have them both work equally well, right? So this comes up, for example, where would you most want this? Well, if you're a soldier and you're in battle, right, and you're using your gun and you bend the barrel, right, accidentally, you can't fire the weapon anymore. What you'd like to do is you'd like to swap out the old barrel and put on a new barrel and continue using your weapon, right? You wouldn't want to have to use a whole new rifle at that point. But that would have been inconceivable in the 1800s, because each barrel had been custom honed to fit into the stock for that particular rifle. So the idea of being able to mass produce a part was the idea of being able to make it, to remove all human discretion, to make it so precisely machined that any two objects from the perspective of a user that came off the same assembly line were identical, right? And that was an extremely hard problem. It was so hard, in fact, that many companies claimed to be doing it when they weren't. The Singer Sewing Machine Company claimed to be mass producing sewing machines, but was not. I think it was Smith & Wesson, I'm not sure, one of the big weapons manufacturers claimed to be mass producing guns, was not. They still was all this hand finishing, and so parts were not interchangeable. The first examples of truly interchangeable parts were actually in bicycle manufacturing. And then subsequently, probably the assembly line that was making Model Ts was actually one of the first major examples of true mass production, where there really was machine automation and production of interchangeable parts. So this was an incredibly hard technological problem. So it's easy if you go back, for example, and read the writings of Frederick Winslow's Taylor, all about sort of time and motion, Fordism. They seem incredibly simple-minded from today's perspective, right? It was all about, you take a guy, you watch the steps he takes at his job, you time them, and then you say, now just go do that again and again and again, and don't do anything else, and don't think. And that was a big innovation in management. And it seems silly from our perspective, but they were trying to get people to imitate machinery. Right? And it turned out that was very hard at that time. But the point I want to make about this actually is this mass production was actually a major unskill biased technological change, right? It involves the substitution of a lot of capital for skilled artisanal labor, and raised demand for relatively uneducated labor that could follow instructions, right? And so, you think about the example of the Luddites, right? People smashing their looms in 19th century Britain because they were afraid that the power loom would devalue their skills as weavers. And they were correct, right? Actually, it did. So the introduction of mechanical looms devalued the artisanal craft of people who had invested their human capital in learning these handicrafts. And so it was the case that basically the movement to mass production displaced a lot of skilled work and raised demand for unskilled labor. So that's why I want to say that that's a kind of probably the most clear counterexample to the idea that technological change is always skill biased, right? Simply not true. Now, as time went on, in the sort of later stages of the machine age, we think that skill demands rose a lot again, right? And that's clear when putting up those figures from the 1940s forward, right? We see this massive increase in skill supply, and yet we still see wage premium increase. And there's a paper by Golden and Katz that links that to basically the growth of high-tech manufacturing. So in particular, things having to do with chemistry, with dairy products, which actually the big challenge there was preventing disease, with creation of with metal products, with liquors, that it required an enormous amount of high-tech capital, which required a lot of engineering. And so, although the actual operation of the equipment was relatively unskilled, the management of production and the engineering of production was highly skill demanding. And so they show that these industries, even at the turn of the 20th century, were already employing relatively large numbers of high-skilled workers. And so, even in the kind of in the middle to later periods of the mass production era, you already see a movement from kind of unskilled bias to potentially skilled bias technological change. And a lot of the technological change in that era probably could be best described as the substitution of fine mechanical activity for human labor input, right? So a lot of mass production is about essentially getting machinery to precisely replicate the activities of skilled workers or skilled artisans, but with much less discretion. And so I think that sort of gives you a sense of the few eras of kind of the relatively recent eras of technological change. And then we sort of get to this age of computerization, and the question is there anything different about computerization from any other era of technological change, right? To say that computerization is a technological change is not a particularly interesting thing to say. We're always confronting technological changes. So what makes a technological change interesting is the degree to which it somehow diverges from what preceded it, right? If it's just a continuation, we don't need any new hypotheses. So So I think that in thinking about sort of what is different about computerization from other eras or other types of technology, it's useful to sort of go back to ask kind of what is a computer. And this is actually, in my view, the example of the first computer, which is the Jacquard loom of 1801. And basically, this was a power loom that was driven or controlled by punch cards, as you can see. And it was quite a brilliant Victorian invention. And what these punch cards did, these were a program that instructed the loom to lift different arms, change the weave, and change the pattern. And it could do quite elaborate things. So there's actually a surviving example of a program for the Jacquard loom that has 10,000 cards, and it weaves a silk portrait of Jacquard himself. And what the Jacquard loom had, two attributes that it had that make it like a modern computer. One is that it was a symbolic processor, meaning that it acts upon stored representations of information, right? And these cards, they could be punch cards. Some of them were tape, right? It wouldn't, like paper tape. It wouldn't matter if they were, made out of cloth or metal, or if they came on rolls, or they came in, if they came in cards. Nor would it matter that this particular pattern does not necessarily have to mean anything specific. You could redefine the language, right? The series of punches to mean different things, and you could still execute them. And so what this was a way of symbolically encoding data for machine reading in just the way when we have a spoken language, right? We all agree what the words mean. They have no intrinsic meaning, right? It's just encoding. That's what symbolic processing is in machinery. So that's one of its key defining attributes, was that it was a symbolic processor, and that is really the central to any information technology. And then the second thing, of course, was that it could carry out these instructions, these repetitive instructions, with incredible accuracy at extremely low cost, right? So once you managed to punch the cards to get the thing done, you could have the machine do it with much greater precision and with much less labor unrest and at lower cost, and you could have comparable workers doing the same thing. Okay, so symbolic processing, B, rapid, accurate execution of stored instructions. Right? Those are kind of the two key defining traits in the way I think about it. And by the way, this thing has quite a legacy. So this punch card was actually the inspiration for Hermann Holrich's punch card reader, which was used to read the 1880 US Census. So he was inspired by the Jacquard loom, and then Holrich's punch card was the inspiration for Thomas Watson, who joined with him to form IBM. And so the sort of modern era of computing begins with the Jacquard loom leading into these other inventions. So in the 200-something years since the invention of the Jacquard loom, or symbolic processing, a number of things have happened. So the most important one is that this has gotten a lot cheaper. Right, so this is from a paper by William Nordhaus. This says 2001. It's actually finally published in the Journal of Economic History, called The Progress of Computing. And he tries to, I don't know if any of you have read his work on sort of the changing cost of light over multiple millennia, right? And he tries to do the same thing with the changing cost of computing over a couple of centuries. And so the x-axis here, the y-axis here, is cost per millions of standardized operations per second, right? Where a standardized operation is one, simple computation of some type or other, right? So it might be adding a number, subtracting a number, and then this is time. So from 1850 to 2010, approximately, and then this is a logarithmic scale. And so if you look here, basically from 1850 to around 1940, there isn't a lot of progress in that, right? So essentially, most of the cost of computing at that time was paying people to do calculations for you, right? So going back to Hermann Otto Hirschfeld and his computers, what he meant was the skilled women who did math on paper for him. And that was basically the technology until about 1940, right? And then the era of the Second World War brought about a revolution in computation because there was a need for computing for cryptography, right, for code breaking, and also for engineering, in particular for design of atomic bombs. And so, for example, the the breaking of the German Enigma machine code, right, by the Brits was done by Alfred Turing, and he was using an early computers that were basically primarily were made from vacuum tubes. Right. At the same time, John von Neumann of the von Neumann-Morgenstern utility function. Right. Von Neumann was the von Neumann-Morgenstern utility function. Probably, I would hope to think was not his greatest contribution to all of science. And von Neumann was one of those guys who could basically memorize tables of numbers at a glance and spit them back at you. And he was really also the designer of the original computer architecture, what people call the von Neumann architecture. And now people sort of call it the von Neumann bottleneck, which is this notion of a central processor through which all information flows. But that's anyway, so in this era, so what you see in this period from 1940 to around the 1950s and 60s is the era of vacuum tube computing, right? Which then gives rise to the era of transistor computing. So a transistor is basically a silicon facsimile of a vacuum tube, right? It's a switch whose activities is controlled by electrical input, right? So by applying input on one pole, you can make it into, you can stop the switch. By taking off that input, you can allow electricity to flow, right? And so that can represent ones and zeros. And then a transistor is basically a solid state version of that, doesn't require a vacuum tube. And then following from the transistor era, of course, is the microprocessor era, which is just the notion of putting, first, tens, then thousands, then millions, and ultimately billions of transistors on a single a small substrate. And that gives rise to huge cost declines in your ability to do symbolic processing and therefore to execute stored instructions with a high degree of rapidity and low cost, right? Okay, so actually, let me just kind of give you a nice. This is actually a kind of a cool example of this. This is an ad for the. This is also again from the Nordhaus paper. This is an ad from the Burroughs Adding Machine Company in 1909, and the ad is called "A Better Day's Work." I don't know if you can see this, but basically, this is adding a column of numbers by a clerk. And this is done the same thing with using a Burroughs adding machine from 1909. Now, I don't know if any of you have ever seen a Burroughs adding machine from 1909. Basically, it's, now I can use my board. It basically, you have the numbers from, I guess it would be, how does it look? You have 12 columns, 1, 2, 3, and then in each of them, you have the numbers 0, 1, 2, blah, 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 through 9. And then if you want to enter a number, you would say, okay, well, if I wanted to enter a number, actually, I guess, sorry, I guess you would put the highest decimal. Okay, so let's remember decimal laws. So it would actually, it would be more useful to think about this as, 12, 11, 10, ones place, right? And then we have 0 through 9, right? And these carry over. So if you wanted to enter the number, for example, 1073, right, this would be your fourth place. You would do a 1 here, a 0, and then a 7, and then a 3, right? And then you would pull this huge lever, ka-chunk, like this, and then you would push the plus button, and then you would enter another sequence of numbers by going down like this, and then you pull it again. So it was a completely mechanical device. It was actually very cool. My uncle gave me one when I was a kid. I wish I still had it. But it was very different from your conventional calculator in the sense that it wasn't just 10 keys, right? It was, and this was again, it was the 10 key thing came much later. But anyway, so this is in this example, you see that this clerk took 9 minutes to do this column of numbers, and I don't know if you can see, there's all these crossouts. And then here is the same thing done by a skilled Burroughs adding machine operator, and they did this in the remarkable time of 1 minute and 30 seconds. And so that would be a 6-fold decline in the time involved in doing this calculation. Now, that's obviously not a fair cost comparison, right? You're paying the clerk some hourly wage. On the other hand, you probably paid a lot for that Burroughs adding machine. So who knows? But it gives you a sense of the potential growth in and productivity in this set of activities, right? And this, of course, this is pre-computer. This is mechanical computing, right? But this would correspond to, this point here in the Nordhaus diagram, right? Okay. So the question is, what's that good for, right? So if you have something that's declining, 1 to 2 trillion-fold in cost, right? There's a very strong incentive to use that productively. But then the question is, well, what can you use it for? And I think the answer, if you think about it for a while, is that it's good for tasks that can be proceduralized, that follow a routine or well-specified set of rules, such that you can take a piece of machinery that has, kind of lots of speed but not a lot of judgment, right, and get it to carry out the task for you. The ideal example is a task to be carried out without any discretion, so the computer doesn't have to stop you all the time and say, well, what should I do now, what should I do now? So you'd really like something you can script completely, such that a machine that has no common sense and no understanding of precisely what it's doing can do the task sufficiently well that you can leave it unsupervised and still expect to get good results, right? So the tasks which this obviously applies to very readily are things that are, that are simple, repetitive cognitive tasks, like clerical tasks that involve sorting or filing or copying and calculating. It involves control tasks like measuring or monitoring a production process. You can think of many examples like this, and so we call them, and I'm sure you've probably heard this term by now, is routine tasks. Now, I want to make one distinction here. When I say routine, I don't mean routine from the perspective of a person. I mean routine in the sense that it follows it's scriptable. It can follow a procedure, right? So, for example, doing a massive computation, right, is not routine from the perspective of my 7th grade children, but is routine from the perspective of a piece of symbolic processing equipment, right? So, routine should not be confused with the notion of kind of mundane, which just means anything that's sort of tedious. Okay, so routine means procedural. Okay. But of course, the question is, well, is there any limitations to what you can do with that? And I think the answer clearly is, if you believe that this is particularly applicable to a set of routine activities, then it means that things that don't fall into that category are harder to computerize, right? So tasks that are non-routine, and at least our way of defining it, you might think of 2 broad categories of non-routine tasks. One would be things that require problem solving, creativity, managing others, and we call these abstract tasks, right? These are tasks that require you not simply to follow a procedure, but also to supply ideas, right? To solve a novel problem, to have some type of an insight, right? So hopefully a lot of what you are learning, what you do, and what you will do in your careers involves this type of activity, right? The other things that are non-routine are tasks that require physical adaptability or non-scripted interpersonal interactions that are not per se complicated and yet are very difficult to automate at present, right? So, for example, there's a reason that your dishwasher doesn't empty itself after it washes dishes, or your vacuum cleaner doesn't walk upstairs to do the upstairs, or if you have a Roomba vacuum cleaner, there's a reason that you have to put that little wireless gate there so it doesn't fall down the stairs, right? And it's not because it wouldn't be good to have a dishwasher that empties itself or a vacuum cleaner that could climb around your house, right? The reason is those are locomotion tasks that require a degree of dexterity and precision and visual interpretation that has proved extremely expensive and difficult to automate so far. Not that it won't be done, right? But it wasn't the low-hanging fruit. Similarly, the reason or if you think about driving, why is the cab driver, right, that drives you through the streets of Germany, why isn't that a machine driving that cab for you, right? The reason is that that processing the visual information to interpret what's happening on a busy city street and respond to that appropriately in real time is something that still is at the frontier of machine automation, right? So if you think about well, why is an airplane, why can an airplane be flown by an autopilot but a cab can't be flown by an auto taxi? Well, the reason is that an airplane is a lot like a train, right? It essentially follows a route in the sky and doesn't require much instantaneous adjustment, right? And that's not at all true for a taxi. Or I don't know if some of you have followed this, but the U.S. Defense Advanced Research Projects Agency, DARPA, sponsored for years a contest to have a robotized car drive across an area of California desert. Right now, this is something that if you had a modern car that was all-wheel drive, you could basically do in the course of a couple of hours. But it was the case for the first bunch of years that every single car that entered would fail. Right, so these are cars that had to act on their own discretion. People could be monitoring them, but they couldn't be driving them remotely. And so they would all variously crash into things or flip over or just start spinning around in circles. It wasn't until recently they actually, a number of teams succeeded in producing a car that could drive, basically in open terrain, right, without any pedestrians, without any oncoming traffic, right, and make it across a couple of hours of desert without imploding. So I want to suggest that that this set of tasks, right, what I'm calling these manual tasks, some call them service tasks, it's not that they defy automation, but they turn out to be very hard engineering problems. And so there's a reason they weren't tackled right away. Okay, so good. Okay, so basically, just to summarize, right, this is sort of a simple 3x3 table. So here's routine tasks, abstract tasks, and manual tasks. So clearly for these routine tasks, right, there's an enormous amount of direct substitution of computer capital for human labor input. And I want to say that although that's an obvious, I think, non-controversial assertion, it's very new in the sense that for most of the history of automation, there was not capital that could substitute for cognition, right? That we had capital that could substitute for physical labor, but for the actual job of manipulating information, of calculating, of looking things up, right, of making computations and arriving at decisions, right, we really didn't have machinery that could do that type of work. That was the kind of mind's exclusive dominion, right? And that's very important because if you think about the era that that proceeded from basically the start of the stage of mass automation or mass production up through the 1970s, right? The occupation that became most important in enabling that type of growth of industry was the clerk. So at the turn of the century, clerks, the people who did those adding in columns, sometimes with crossouts, were highly educated workers. They were high school educated, which was highly educated at that time. They were well paid. They were all males as well. And basically they were people who were you could think of them as kind of the production workers of the information age, right? They were people who would do the bookkeeping and the calculating that allowed for organizations to be large and consistent and well managed because they had control of all of the information that was required to produce complex objects, to ship them to various markets, and so on. And before that, the organization of work was much more chaotic. What starts to happen in the 1970s, and much more so in the 1980s, is that type of job that had become extremely important in enabling a whole era of automation, right, becomes now much more substitutable by technology, right? So that's a very different type of technological change, I want to argue. Okay, now moving on to these others, obviously for these abstract tasks, these problem-solving tasks, mental flexibility tasks, we think there's much, much less scope for substitution, and in fact it's quite plausible to argue that there's strong complementarities there, right? That basically, if you're in a profession that uses information intensively, if you're a doctor, if you're an attorney, if you're an economist, if you're a scientist, right, the availability of cheap information processing, right, is valuable to you at the margin, right? That is potentially, you might say there's a kind of a p-complementarity between declining price of information processing and the sort of value of output or value of the productivity of people in the professions, because having access to better information makes you more effective at your specific task, right? So you could argue, I think, that there's a complementarity there. But then this, I think, is the kind of, not anymore surprising, but was surprising at the time, was this notion that a lot of these low-skill tasks, right, what we think of as low-skill, because they're non-routine, are not are kind of left behind, right? There's limited scope for direct substitution of capital for labor in these, truck driving, security guard, waiter and waitressing jobs, nor is there necessarily very strong complementarity, right? You don't see, it's not, you can give examples, right? You can say, oh, well, GPS makes truck drivers more, gets them to their routes faster, and, electronic vacuum cleaners make, janitors slightly more productive, but there's nothing like the strong complementarities that you see in this abstract realm. Okay, so the reason I kind of belabor these points is what I want to underscore, and I'll come back to this in a second, is that these task activities are not monotone in skill as we typically think of it, right? So in particular, this is data from the U.S. and we've tried. This is based on the work with Levy and Murnane, and we tried to categorize things into these manual and abstract and routine tasks. Now, let me say how we did this. We were using something called the Dictionary of Occupational Titles, which is an old instrument that put out by the U.S. Department of Labor starting in the 1930s to measure the skill requirements of jobs. It has since, thankfully, given way to a probably more modern instrument called the ONET, or the Occupational Information Network, that has better measures. Although none of these are as good as measures that are available in Europe. So, for example, the stuff that Alexandra has used from the IAB data to look at job tasks, those are measured at a person level, right? And you can look at the changes in those over time. So those data are much, much more compelling than the U.S. data, right? So I think this provides a starting point, but by no means provides the most precise or informative measures. But anyway, just starting from here, what you can see is if you look at these manual tasks, as you would expect, right, they're most prevalent among high school educated workers, high school dropouts and high school grads, some college grad. Abstract, just the opposite, as you would anticipate, right? So highest among the most educated, lowest among the least educated. And then these routine tasks actually are concentrated among people with high school graduate degrees and some college education, right? And so the substitution of technology for routine tasks, if you think it's going on, right, is actually not going to tend to substitute for the tasks done by the lowest educated and least skilled workers, but it's going to have an effect on the occupations closer to the center of the skills distribution. Okay, now this is why I think it's really useful to make the distinction between tasks and skills, right? Because if you think about it, right, think about, for example, if you're a worker with some college or high school education, right? Probably come around 1980, you're in a job that's relatively routine task intensive, right? You're an accountant, you're a clerk, right? You're doing things that are pretty well paying at that point. And then as time goes on, there are fewer and fewer of those occupations, or fewer of those opportunities, right? Now, it's not the case that those people are stuck in these occupations, right? Presumably, they can move into these occupations, right? If you can work a typewriter, if you can work a phone, you probably can serve a meal at a restaurant, right? So it's quite likely that you would tend to see people moving across tasks, right? Even holding education constant. Right? So in thinking about this, it might be adequate to say there are two skill groups. That, you could say the high skilled and low skilled, but their relative productivity in various tasks is going to differ, and people are going to tend to self-select or move across occupations in response to the changing demand for different types of activities, right? And so this example, or this way of thinking of it, puts focus on occupations as measures of tasks rather than skills as measures of labor market demand per se. So let me come back. Okay, so let me do a few things. I realize I've spoken much too long. But first of all, I just want to actually give you one very graphic example of a type of automation that I think is extremely interesting. So this refers, I'm going to actually show you a movie. maybe I can even put my microphone there. This is an example of a robotic warehouse. So, as many of you know, in the online era, right, there's a huge growth in warehousing of goods, right? That basically you have direct shipment from warehouses to consumers. So in the U.S., for example, Amazon or Zappos, they have these multi-million square foot warehouses basically in the cheapest parts of the countries, right? So where land is cheap and you're near an airport. That's what you want. And land is cheap and labor is cheap. And then you have hundreds of workers who basically run through these warehouses with little handheld computers in so-called pick waves, where they go and they pick the objects off the shelves and then bring them up to the front for boxing and shipping, right? And it's a very labor-intensive activity. It's relatively expensive. One thing that makes it expensive, well, several things. One, laborers themselves. Two is you have to air condition these warehouses, and they're millions and millions of square feet, so it's actually extremely expensive. And three, they make a lot of errors, right? They get the wrong object. And if they ship the wrong object, that's a problem for customer service. If they don't, it still has to be restocked. And so there's an effort. And now, why is that task, of course, why is that being done by humans? Well, it's a non-routine task. What's non-routine about it? Well, it's actually just sort of the manipulating, moving among shelves, recognizing objects, picking them up, and carrying them, right? That's the kind of the non-routine manual task about it. So there's a company called Kiva. It's a robotics company that's trying to, automate a large part of that process. And you'll see that their method of automating it essentially involves making this non-routine task routine. So let me go to that example. Okay. See if we can get it to go. And if this is broadcast, you sort of hear that, right?
Kiva uses a breakthrough new approach to order fulfillment, one that simultaneously improves productivity, speed, accuracy, and flexibility. With the Kiva mobile fulfillment system, the operator stands still, and products, cases, items, or orders come to them. Pallets, cases, and orders are stored on inventory pods that are picked up and moved by a fleet of mobile robotic drive units. The distribution center is now completely dynamic, self-organizing, and self-adaptive. The first step is restocking. A pallet of products arrives in the building and must be put away in the picking area. With a typical solution, the worker must find out where the location of each of these cases is in the distribution center and wander out into the warehouse to manually place them back into their racks. But with Kiva, when the worker scans the inventory for replenishment into the system, the drive units immediately begin moving to bring the correct pod for replenishment. The worker will not move from this spot to replenish all of these cases. By eliminating operator travel, Kiva increases productivity. In addition, since the system dynamically calculates the optimal location for replenishing the product, Kiva eliminates the need to analyze and reslot inventory. Once the inventory is in the systems, workers can pick items to fill customer orders. Part of the Kiva mobile fulfillment system is a server that is integrated with the customer's warehouse management system. This server receives the customer order and assigns it to a picker at a station. These orders will be filled in real time, unlike other systems that require batching orders together before they can be filled. As soon as the order is assigned, drive units are dispatched to retrieve the inventory required. Each worker is supported by 5 to 10 drive units that will line up and wait their turn to be picked. The worker stays in one place and lets the work come to them. As a result, each worker can produce 2 to 3 times as many orders per hour. The first pod to arrive is the shipping pod. This pod holds the box that will be shipped to the customer.
But there's a laser pointer that is pointing to the objects on the shelf. So that what the worker does is the drive unit drives up with the shelf, the laser pointer points to it, and then the worker just picks it off the shelf, scans it to make sure that they've picked the right thing, and then puts it in the box, right? So, what is the division of labor here that's going on, right? Well, the division of labor is, you can think of warehousing as being a mixture of several different types of tasks. right? One of them is an information processing task where you're basically keeping track of where things are, right? Allocating them, picking up orders as they come in, dispatching them efficiently, collecting this stuff, right? Most of that is purely about movement of information, but then there's the movement of the physical goods. And the movement of the physical goods requires a mixture of sort of, carrying stuff across warehouses, which is easily done by these automated shelves, and then actually picking up the final object and putting it in a box, which is a hard problem for engineering right now. Right? So basically what has been done is every part of that process that can be mechanized at feasible cost has been, right? So the information processing, the movement of objects around the warehouse, what's left, the very last thing to do is to pick the thing off the shelf, right, and put it in the box. And of course the Kiva system is saying, with a laser pointer, pick that up, put it in the box, right? So and actually it's this goes back, this is a slightly dated, but I think it's actually a potentially good example. When I was a kid, it was long before most of you were born. In the sort of the era of the space race, right, between the Russians and the U.S. And my father used to tell me this joke. He's of this cosmonaut is getting into the Soyuz capsule, and they seat him in the capsule, and they put this monkey on board, and they said to him, okay, so when the red light goes on, that's instructions for the monkey. When the green light goes on, that's instructions for you. So they both get in, and the red light goes on, and it says, secure capsule, close, hatches, check engine pressure. So the monkey does all these things. The cosmonaut's just saying there, and then it says, okay, countdown, fire main thrusters, achieve brake, exit velocity, and so the monkey does all that. Red light, red light again, jettison. Jettison fuel tanks, prepare for deep space orbit, and the monkey does all that, and then and finally the green light comes on and it says feed the monkey, and the Kiva system has a little bit of this feeling to it, and I don't mean to disparage it, but it was simply to point out that what these workers are left to do, right, there's demand for it, right? There's demand for feed the monkey jobs, but they're not going to be high-paying jobs by and large, right, because the supply of people who can feed the monkey is pretty elastic, right? There's a lot of people who can do that type of work. And so this type of framework says you might expect to see a lot of growth in relatively high-skilled abstract tasks and relatively low-skilled manual tasks. What's that going to do to wages depends a great deal, right, on how the labor market functions, how much people need to be compensated for those activities, what are the set of institutions that determine them, and also what is the nature of consumer preferences over outputs produced by these different goods and services, right? So, for example, go back to the old, this is the famous example from Baumol about haircuts, right? Haircutting is a technology that really hasn't had much productivity improvement over time. Right? It's the case that barbers now do pretty much what barbers did 200 years ago. They may have electric shears, so that maybe they're somewhat more productive, but basically not much, right? And yet their wages have risen with the wages of the rest of the economy, right? And it's not because their productivity has risen. So it must be that we must value haircuts enough to compensate people to keep doing that work, right? Even though they're not getting better at it, because if we didn't compensate them enough, they would do something else. Right? So in some sense, if something is becoming more expensive over time because it's basically a technological laggard, right? Whether it continues to be produced depends on the sort of essentially the consumer preferences, ability to substitute between that and other objects, right? If haircuts have got sufficiently expensive, right, people wouldn't cut their hair, or they do it themselves, right? And so similarly for these types of tasks, what they're going to pay ultimately depends on how much those outputs are not substituted by another set of activities. Okay, so let me give you a few more examples on this, and then in the next section I'll actually go through some of the analytics of this more thoroughly. Okay, I'm not sure where to start. So first of all, this is the This is just from the Otto Levy-Murnane paper. We try to measure the prevalence of these tasks across in the U.S. economy over multiple decades, right? And what you see is these abstract tasks that you might most associate with the professions, right, are rising in prevalence, and they have been for decades, right? That's nothing new. Maybe they accelerated, maybe not, but clearly, these types of professional activities have been becoming more important over time. More interestingly, these routine tasks, as I said, are growing more prevalent in the 1970s, plateau, and then start falling very rapidly from the 1980s forward. And that's really, and a lot of that is driven by the decline of clerical occupations and things that look like that. And then the third thing is these manual tasks, right, this kind of manual labor, and that has been on the decline for a long period of time, but that decline actually starts to plateau, and in fact in the most recent years actually increases, right, and that picks up. And so, in the broad sweep of things, you can see this starting to happen. Let me give you a couple more examples. Okay. So this is, again, looking at US data. This gives you the growth of employment shares by major occupational groups from 1980, just the last 25 years. And these basically can be thought of, these managerial and professional specialty occupations. These are the high-skilled, high-wage occupations. These are the kind of next category. And then these are all of the production jobs. This is farming jobs. And then service occupations are these kind of in-person things that I mentioned. So waiting tables, house cleaning, low-skilled medical care, and so on. And if you look, the only two categories that are adding employment as a share of all occupations, right, are one, these managerial and professional specialty, and the other is these service jobs, right? If you focus specifically on non-college workers, right, workers who have high school or lower education in particular, you can see that the only category that's growing in size is the service occupations, right? This is the only part of the only type of occupation that's actually adding employment among low-skilled workers. And there are really two things that are particularly important about service occupations that I think sort of fit this idea. One, as I've mentioned, is that they're difficult to automate, right? I hope I've already stressed that point. The other thing, of course, this is extremely relevant, is these things are very difficult to outsource or trade, right? Which is a point that's been emphasized by Alan Blinder, right? That they need to be done in person. Most of these things actually are not storable, they're not transportable. In fact, many of them involve the physical laying on of hands by the worker on the customer, right? So if you're cutting someone's hair, if you're doing medical care for them, you actually have to be there in person. Now that may not always be true, right? It might be possible, for example, that you'll go into a barber and a sort of a telepresent hair cutter in Vietnam will cut your hair, right? Already that's being done with sort of remote surgery, so it could eventually be done with a lot of other services, right? But at the moment, sort of the proximity constraint is pretty salient. And yet, of course, as I stressed, these things require very minimal education, and so there's a lot of labor supply to them. And let me actually show you, this is the last figure, and then we'll take a break. Okay, so this shows you the U.S., as I said, the U.S. employment by occupational mean wage, this U-shaped pattern that you see from the period of 1990 to 2005. I'm now going to take that figure, and all I'm going to do is I'm going to weight down service occupations to their 1980 employment share. And what you see is that, in fact, almost all of the growth, almost all of that U is coming from the growth of this particular category of relatively low wage, low education employment, right? And so if you want to understand this polarization phenomenon in the US, and it turns out in most other countries, you actually need to understand what's driving the growth of that type of occupation. Okay, so let's take a break and we'll come back to the sort of more rigorous evidence on this in the next period. Thanks.